Good afternoon, everyone. We are from the course MDB 4313Z Flow Assurance in Pipelines and Flow Lines. We are here to present our project titled Estimation of Erosion in Oil and Gas Pipe Elbow Due to Sand Presence. Thanks to our supervisor, Dr. Jutika Chandra Kurnia, who helped us and guided us throughout this project. And thanks to our fellow members and my group mates also. So I would like to start my presentation. These are my team members, which are the leaders SURESH SANDRASAGAR, and me, KAYILASS NAIR, and followed by HARIHARAN GANASEN and also JAGROSHAN. So I would like to start with the executive summary of this whole project. This group is tasked to investigate the occurrence of erosion in 90 degrees elbow pipe. The scope of our project starts with pre-processor and post-processor and solver as a numerical approach using computational fluid dynamics used for the study, also known as CFD. I will start with the introduction part, which is the case study. In the oil and gas industry, the extracted oil and gas from the well is inhabitable, polluted with solid particles, such as sand. So, this sand in particular is a source of several flow assurance problems. One of them is erosion damage to the pipelines known as elbows and several other control equipments. If this erosion is not properly monitored or predicted, the entire production processes can be hampered or even shut down for an extended period of time. So we try to do with the computational fluid dynamics software with erosion model was applied to estimate the average and the maximum erosion rate in a 90-degree elbow. I'll start with the problem statement. So in multi-phase flow, transporting solid particles in oil and gas flow can cause erosion damage to the pipeline and fittings. Moving on to the objective. The objective is to focus on how the particles impact the velocity in the pipeline and the maximum and average erosion rate in long 90 degrees elbow. Next, the scope of study. The scope of study is to identify the critical parameters for erosion rate due to sand and to investigate the effect of maximum erosion rate using these parameters.
By the effect of strong particles, which we are using is sand, which is suspended in streams, maybe in fluid, gas or multi-phase streams, on a strong divider or limit. Strong divider or limit such as pipe fittings, 90-degree elbows and other junctions of the pipe. So going to the next slide by Y.I. Oka. His title of book, Impact Angle Dependence and Estimation of Erosion Damage to Ceramic Materials Caused by Solid Impact. In his book, he did a comparing of erosion behavior of metallic and ceramic materials, and he has found that the erosion rates at an impact angle of 90 degrees were slightly related to the hardness or fracture toughness of ceramic materials, but were not direct indicators of erosion damage for the various ceramic used in this study. J.G.A. Beaton 1963 in a study of erosion phenomena. His paper, he did equations and then he has done several erosion phenomena explained through formula, and indications are given for preventing or reducing erosion in practice. Going on to the third book by I.M. Hutchings, 1981, A Model for the Erosion of Metals by Spherical Particles at Normal Indents. The data obtained was by experiment with aluminum alloys, as well as previous published data are compiled with the theory. In conclusion, a theoretical analysis is presented for the erosion of metals by spheres at normal indents. Going on to the last book, which we did a research by Y.I. Oka again on the title Practical Estimation of Erosion Damage Caused by Solid Particle Impact Part 1, where he says about the effect of impact parameters on predict methodology. I will explain to you on modeling the product, or known as the component. The 3D pipe was a 90-degree elbow fitting whereby it was modeling using the ANSYS Fluent software, as shown in the figure below. The component was modeled in a 2D sketch. The interface used during modeling process was reference lines, butterfly upper and lower sides with angles of 135 degrees and 15 cm from the pipe geometry, sweep circle of outer diameter to generate the 3D sketch of the pipe, and all sketches of body selection was made into one part. So after modeling the product in the geometry, we here can move by into 3.2, which is the meshing. In the meshing, the selection I will explain to you the steps of how the mesh was generated using ANSYS Fluent. The mesh generated was used using the sweep method at first, where we did the overall meshing for the whole pipe, and then for the edges and inner parts of the pipe, we use size meshing. And the number of elements for the meshing that we used was around 543,803 elements. So once the meshing has been done, we can now go into the stimulation, whereby the fluent settings for the inlet, we did a velocity of 20 to 30 meter per second. The outlet, we named it as pressure outlet. The wall had no slip condition. Turbulence was on K epsilon and K epsilon was in dpm. For the injection surface, the velocity we set was 20 to 30 meter per second of diameter of 100 to 200 micrometer. Density of fluid was 1340 and 1410. The flow rate was around 0.5. For the discrete phase, we set the velocity to 20 and to 30 meter per second with the density of 920 kilogram per meter cube. So that's all for methodology.
So today I'm going to explain about the results and discussion of our project. So actually we know that velocity, particle size and particle density are the three main reasons for the increase in erosion rate. So let's go into more depth in our results and discussion part. So first of all, I would like to explain the effects of particle size on erosion rate. Actually, it is significant to study the effects of particle diameter of fluid-solid interaction, as particle size in different systems varies to a large extent from nanometer to centimeter. The particle diameter has direct influence on drag force and therefore affects the flow behavior. The influence of particle diameter on total erosion rate on surface of was studied by changing the particle diameter from 100 micrometer to 200 micrometer. The influence of particle size on the maximum erosion rate was represented in table 4.1. As seen, the maximum erosion rate is closely related to the fluid velocity. This figure also indicates that the rate of erosion augments linearly with the particle diameter. The maximum erosion rate is recorded at 200 micrometer for velocity of 20 meter per second for both density, which is 3.84 times 10 to the power of negative 26 and 3.61 times 10 to the power of negative 26. So moving to the next part, this is our simulated results obtained from ANSYS. As we can see that for particle size of 200 micrometer for same density, the erosion rate is higher compared to the particle size of 100 micrometer. Same goes to the density of 1410 kg per meter cube. The erosion rate for particle size of 200 micrometer is higher compared to the particle size of erosion to the particle size of 100 micrometer. So moving to the next factor will be the effects of velocity on erosion rate. So in order to investigate the impact of velocity on the maximum erosion rate, several inlet velocity was simulated, which are 20 meter per second and 30 meter per second. The impact of inlet flow velocity on the total erosion rate is being demonstrated in table 4.2 for particle size of 200 micrometer. So the reason why erosion occurs in a pipe when there's an increase of velocity is because there's an increase in relative velocity between the crude oil with sand and the surface of the pipe, which cause fluid shear. So the trends are observed to be maximum erosion rate at two various particle density at 200 micrometer when velocity is 30 meter per second, which 4.31 times 10 to the power of negative 26, and for this one 4.14 times 10 to the power of negative 26. Thus, when velocity is increased from 20 to 30 meter per second, the maximum erosion rate increased by about an order of magnitude. So this will be our simulated results. So we can see for the velocity of 30 meter per second, the erosion rate is higher compared to erosion rate for 20 meter per second. Same goes to this. When the velocity is 30 meter per second, the erosion rate is higher compared to the erosion rate for velocity of 20 meter per second for density of 1410 kg per meter cube. So moving to the next factor will be the effects of density of particle on the erosion rate. So as we know that particle density mostly influence the erosion by determining intensity of particle impact on a surface. So as we can see the table 4.3, we can deduce that the erosion rate tends to decrease when the density increase. This is because high density particles tend to move slowly or settle out of the carrying fluid, and therefore they are unlikely to do much harm. So moving to the simulated result, as we can see that the erosion rate for density of 1340 kg per meter cube at velocity of 30 meter per second, the erosion rate is higher compared to the particle density of 1410 kg meter cube for velocity 30 meter per second. So that's all from me. Thank you.
Finally, I would like to conclude about this. To conclude, the density, velocity, and the particle diameter size can effectively influence the erosion rate of the pipe band. So, increasing the pipe diameter can reduce erosion and extend the service life of the pipe band. But we couldn't do that because all these pipe diameters and the sizes are following the SB standard of our oil and gas industry. The maximum erosion location is sensitive with the change of the band orientation, pipe diameter, and inlet velocity. So this shows when all these parameters are increasing, the erosion rate increases by its time. That's all from us. Thank you very much for listening to us.